This is the video for Westlake Chemistry's Unit 18 lecture over the Introduction to Nuclear Chemistry. Before we start really getting into the nitty-gritty of nuclear chemistry and talking about all the parts, we're going to do a quick review over the structure, the basic structure of an atom. You learned this way back in the first semester around Unit 3, but just as a very quick reminder, we have in the atom a nucleus in the very, very center surrounded by electrons. And inside that nucleus are our protons and neutrons. The atomic number, which is abbreviated Z, is the number of your protons. And the mass number, in other words, the total mass of your atom, is the number of protons plus your number of neutrons. So essentially, your atomic number will tell you what your element is. The mass number tells you how heavy it is. Last but not least, there was this term you learned a while back, isotopes. Isotopes are the multiple atoms of the same element, which means they have the same number of protons, but different mass numbers. So same number of protons, so therefore the same atomic number. That makes it the same element, but they have different mass numbers, which means specifically they have different numbers of neutrons. When we start writing isotopes and specific information about elements, there's a couple ways we do that. Again, you've seen a lot of this before, so it might not really, the more you see it, hopefully it's starting to come back to you. We have the element symbol that we can write, and on the top number, we always put the mass number, which again is protons plus neutrons, and the bottom number is your atomic number, which is just your number of protons. Therefore, your top number should 99% of the time be bigger than your bottom number. The only time it's not bigger is when they're the same. So there are a couple of rare instances where your top number and bottom number is the same. Most of the time, your top number will be your bigger number. It will never, ever, ever be smaller than your bottom number. So that's really important to keep in mind. On the bottom, another way that we can write our elements and isotopes are by saying their element, their actual element name, and then including the mass number after it. We don't feel the need to necessarily always put the atomic number, because if we tell you what the element is, lithium, you should be able to remember, okay, lithium is Li on the periodic table, and on our periodic table that you're provided, you can look up the atomic number. So even in that top section with the symbol and the mass number and atomic number, there will be times where we don't even give you the atomic number. We expect that you can look it up at the periodic table and find it if you need it. So this entire year, up to this point, we have spent all of our waking moments in chemistry class working on chemical reactions, where atoms rearrange to form a new substance, but every atom keeps who it is as an atom. So you always have the same number of carbons at the beginning and the end. You used to have the same number of hydrogens at the beginning and the end. Now you can move them around. You can make new ratios to make new compounds. But at the end of the day, all the atoms you had at the beginning, you have at the end. No big change to the atoms themselves. When you do your chemical reactions, you are working with those valence electrons, those outer electrons going back and forth. You never really touch the ones on the inside, and you certainly never touch your nucleus. And you're really only been dealing with small amounts of energy. Now, you don't really have a good context for big or small, but understand that all of these chemical reactions you've seen in labs or on paper have actually been relatively small amounts of energy. All of Unit 18 is all about nuclear reactions, where isotopes of one element turn into isotopes of a new element. In other words, I might start with carbon and end with nitrogen. All of those rules of balancing, a lot of them at least, kind of go out the window, because your atoms can now change from one into another. Your nucleus is what is reacting. Electrons can occasionally be evolved in certain ways, but the big target, the big thing that we're making changes to now, is that nucleus sitting in the center of your atom. Realistically, all nuclear reactions involve huge changes of energy. Everyone has seen and knows the formula E equals mc squared, Einstein's famous equation. That's the formula that we use to determine orders of magnitude of energy for nuclear reactions. It is scales upon scales larger than any chemical reaction that we've ever talked about. So a big feature of all nuclear reactions and nuclear chemistry in general is the idea of radioactivity. You've probably heard the term radioactivity before, or radioactive, for obviously it's an Imagine Dragons song, and it's a pretty big idea in pop culture. But the real idea of radioactivity is what occurs when your nucleus breaks down and it spits out little bits of matter and little bits of radiation, little pieces of electromagnetic energy that comes directly out of the nucleus as it changes, because I don't want to say as it falls apart, because that's only half of the nuclear reactions we're going to be talking about. So anytime you have a nuclear change inside your nucleus, there is a high likelihood you're going to release some energy or release some particles. Those small particles or energy release is what radioactivity is. So on that topic of radioactivity, a very, very brief history. If you want the full history, go talk to your teachers. They will be happy to give you a more full story behind radioactivity and the pioneers behind it. But the three biggest names in radioactivity were Henry Becquerel, Marie Curie, and her husband Pierre Curie. Between the three of them, they were able to discover what radiation is, a few examples of elements and compounds that gave off radioactivity. Henry Becquerel is noted as the person to originally discover radioactivity. Essentially, he discovered that uranium could give off light after it was exposed to sunlight, but that not only does it give off visible light, there are also invisible X-rays. And he proved that using photography materials. Marie Curie and Pierre Curie also furthered his research, discovering two elements of their own, radium and polonium, and together the three were given the Nobel Prize in Physics in 1903 for discovering radioactivity. Between the three of them, there's some brilliant stories, including scientists that we're not going to mention here. Like I said, feel free to go ask your teacher, and they would be happy to give you a more thorough history if you just want to hear some cool stories. But I promise there won't be any questions about any of those stories. So how do we know which elements are radioactive? Well, the more unstable your nucleus, the more prone to radioactivity you will be. So the smaller your atom, the more stable it's going to be. So you're looking for this nice ratio of protons to neutrons. The closer you are to 1-to-1, the more stable. When I say 1-to-1, what I mean is for every one proton, you have one neutron. The closer you are to that ratio, the more stable you will be. The more stable you'll be, the less likely you're going to be to what you as an atom would be to be radioactive or have radioactive tendencies. So the most stable elements are those from 1-to-20, because those stay closest to that 1-to-1 ratio. As you get bigger and bigger and bigger, realistically, you become more and more likely to be radioactive. Everything above element 82 is unstable to some degree. They are always slightly radioactive. Now, when I say slightly radioactive, they could be very, very, very slightly radioactive, but they're all at least somewhat radioactive. There are 5 radioactive particles that we are going to deal with as we move through Unit 18. Those 5 are listed right here. Alpha particles, which are essentially just helium atoms. They have a mass of 4 and a proton number of 2. And we use either the Greek alpha symbol, or we just could call it a helium atom. Again, alpha particles are basically just helium atoms. There's also electron particles, or beta particles, and electron particles are exactly what they sound like. They're electrons. They have a mass of 0, just like an electron would, and a charge of -1. In other words, they are the opposite of a proton, and we can either use the symbol E or the beta symbol. Neutrons are also pretty prevalent in radioactive particles. You've seen this one before. It's just a mass of 1 with a charge of 0, because there are 0 protons, and we use the lowercase n. Jumping to the end for a brief second, protons, you know what protons are. They have a mass of 1, because they have a mass. They have a charge of 1, because a proton is a proton, and we can either use a hydrogen symbol or the lowercase p for proton, because a hydrogen atom is just a single lone proton. It's the same hydrogen that we were talking about in Unit 16 with acids and bases, that donating of a proton from one element to another, or from one compound to another. The only really new particle you'll see here is gamma. Gamma is a type of particle that has no mass and no energy, no mass and no protons, so it has a mass number of 0 and an atomic number of 0. It is pure energy. So it's just a very, very concentrated high beam of energy, and we use this little upside down wavelength symbol, or gamma symbol. Looks like a Y with a little tail. So you will need to know all these particles so that you can work with nuclear chemistry. So the core principle behind nuclear chemistry is this idea of transmutation. In other words, that you could take one chemical element and turn it into a new element, something that was different before. Transmutation is a very old word. We've had it, you see examples of it in history for a very, very long time. Transmutation was the core principle behind alchemy, of scientists who wanted to turn one element into another, specifically scientists who wanted to take lead, which was viewed as a pretty much useless and valueless metal, and turn it into pure gold. In nuclear chemistry, we actually can do transmutation, or a form of transmutations, because we can turn one element into another by changing the atomic number. And as soon as you change that atomic number, you create a new element, and therefore you have technically done alchemy. All right, so in your notes you should have a giant table of different types of radioactive particles and different ways of looking at how they can affect and change nuclei. You should have 10 lines, 10 blanks. There's one here. Yours is actually already done. I'm going to show you how we did it so that you can now turn around and do the 9 for yourself. Of those 10 reactions that you see in your notes, there are 5 of each kind. There are absorptions and captures, and decays and emissions. And then 2 for each type of radioactive particle. So 2 times 5 gives you a total of 10, 5 absorption captures, 5 decay emissions. Essentially, there's just the two words that you'll see for every kind of radioactive radiation, nuclear reaction, tells you what particle you're dealing with and which direction it's going, whether it's coming into the nucleus or leaving the nucleus. So for this first one, beta decay, we have a beta particle, 0, negative 1b, or remember a beta particle is also an electron, so that one would be equally good. It has a charge of -1, it has a mass of 0, hence matching its mass in atomic numbers. And an example reaction of a beta decay, you have a beta particle that leaves, because it's decay, so it would actually be a product, and you would create a beta, or an electron, on the product side. The whole goal of nuclear reactions is to have the same total mass on each side, before and after, and the same total atomic number on both sides, before and after. So as you can see there, you have 14 on the left, 14 plus 0 on the right, 14 and 14. Total of an atomic number of 6 on the left, and on the right side you have a 7 and a -1 combined to make 6. So it's a different kind of balancing. We're not necessarily balancing atoms, we are now balancing actual subatomic particles. So you see there is a change, there is no change in mass, but there is an increase in Z. It goes up 1 because you lost a -1 charge. Therefore, yes, it is a transmutation. If one of the, if your number of protons change, that is your transmutation, because the idea behind a transmutation is that your element has been changed. So in other words, you have a new element that you didn't necessarily have before. So if you have a change in Z, you have done a transmutation. Take some time, see if you can fill out the other 9 on your own. If you're stuck or if you're confused, please come see us so that we can kind of show you and guide you how we do our nuclear reactions. So from here, you should be able to start working through the POGIL, reading, answering questions, synthesizing information through page 7. So you should pause the video here, and you should start working through that. Once you've completed up through page 7, you can come back to this video, and we're going to kind of finish up reviewing the big picture items from it, and making sure we have a good understanding of the basics of nuclear chemistry. So here we have a couple examples questions where you have to write out a nuclear equation using symbols for the following. So I want a nuclear reaction that shows the beta decay of oxygen 15. So we start with oxygen 15, tells us we have oxygen with a mass of 15. The atomic number of oxygen is 8, because that's what it is on the periodic table. We know that we have a decay, so our beta particle will be on the right side of my nuclear reaction. So a beta particle has a mass of 0, a charge of -1, and again, you can either use the beta symbol or the electron. For balancing, I have a total mass of 15. Well, in order to have a total mass on the right of 15, well, I got to have 15. That way 15 plus 0 gets me 15. On the bottom, on my atomic number side, I need to add them up so that I get a total of 8. So I have -1, which tells me that my mystery number is going to be a 9. So I know my mass number and my atomic number to be 15 and 9. That way they're balanced on the left and the right. The fact that we have an atomic number of 9 tells me what my element is. And you should take a second to go look it up if you don't know it off the top of your head. If you do, that's awesome, but you'll see that it is fluorine. So beta decay of oxygen 15 actually turns an oxygen atom into a fluorine atom. Let's look at the next one. Write an equation showing gamma decay of uranium-236. So we're going to start with a isotope of uranium, specifically one with a mass number of 236. And if you look at the periodic table, you can find uranium has an atomic number of 92. It's on that bottom row. It's a decay, just like number 1. So that tells us that our particle is going to be as a product, and it is a gamma particle, which is a particle of pure energy. Now to balance out our equation, we have a total mass on the left of 236. So far I have 0 from my gamma, so in order to make those balanced, I have 236. I have an atomic number of 92 on the left. On the right I have a 0, so that gives me an atomic number of 92 on the right. So realistically, there is no change in atom. The nuclei doesn't really change. It's still a nuclear, it's still a nucleus of uranium, but realistically what you have is a nucleus that is less energetic. This one on the left was at a higher energy. It spit out some extra energy and fell to a lower state of energy on the right. But the nuclei didn't change, therefore it is a nuclear reaction because you changed energy, but it's not a transmutation because you didn't change your element. Take a second, see if you can answer number 3 on your own, just to confirm that you do in fact have a good understanding of nuclear reactions. All right, if you did it correctly, you would have something that looks a little bit like this. Bismuth 209, gate capturing a proton. The fact that it's a capture tells me that my particle is a reactant this time. And turning into an isotope of polonium. So your mass number goes up by 1 and your atomic number goes up by 1. A big idea, and one of the ways to kind of work on these, is to remember that an absorption or a capture, your particle is a reactant. Decay and emission, your particle is a product. The last big idea is the idea of a nuclear decay chain. Essentially, a nuclear decay chain is just a series of steps, a series of nuclear reactions where you make something in one step and then you use it to do another nuclear reaction in the next step. So you become a literal chain of chemical reactions. We will give you the series of steps that we want you to do, and then you show that step one to the next. So here is your example. Write out the nuclear decay chain for uranium-235 given the following series of steps and place the final product in a box. So this time I want you to start with uranium-235. Has a mass of 235 on the periodic table, has an atomic number of 92. The first step is in alpha decay. So it's going to spit out an alpha particle, and it's going to balance. So that, again, we're counting our masses on both sides. They both add up to 235. They both add up to 90. So we turn our atom of uranium into an atom of thorium. That's step 1. Then you're going to do another one. Well, the next one we're going to do is a beta decay, because that's the next one in our list. So we're going to spit out a 0, -1, which doesn't change our mass, but does change our atomic number. There's step 2. Next, we're going to do a proton decay. So we're going to spit out a proton and change our mass accordingly. Back to a thorium. Then we're going to do a gamma. We're going to spit out a gamma particle, which doesn't actually change our element. And last but not least, one final beta decay. And we end with PA with a mass of 230. So you can kind of see, you just take it step by step. Here was step 1, step 2, step 3, step 4, and last but not least, step 5. They are all decays, so all of your particles will always be products. That essentially is the skills that you need out of that POGIL. The only thing that we didn't mention here is how we identify different types of dangers and penetrating ability and harm. All radiation is harmful, but how far it penetrates and how much damage it can do is dependent. So please make sure you have an understanding of that based off the POGIL, because you will absolutely see some questions about penetration ability and damage that different radiation can do. If you have any questions, remember you can always come in and see your teachers. We'll be happy to answer any questions you might still have.